start firing them. So I'm going to get back out of the way a little bit and let you guys have a discussion.
I have a question for John. Both you and the folks who are the that offered the Public Water Agency perspectives leaned heavily on a set of 4 or 5 pretty intensive modeling and statistical studies that were done in the last 5 years or so, the McNally, Thompson paper, and so on, to support your what you see is happening in the Delta with respect to flow. And I think my question is, because, and I guess it's a question for you folks as well, because you have leaned heavily on those, do you think it's useful to do more of that, to do more studies like that are essentially modeling studies with existing data, with increasingly more sophisticated models? That's my question.
I'll go first and then let my friends jump in here. I actually don't feel like I'm leaning heavily on those studies, because my point there is that the two things. One, the studies appear to be in agreement to a certain extent. You know, the degree of emphasis that they would put on exports differs. The fact that they find exports to be an important factor seems to be pretty consistent. My point in presenting those papers is sort of the amazement that you would detect abundance effects for delta smelt due to any one particular factor. I think that the data on salvage this is not a good sampling device. Delta smelt are a difficult fish to sample, and it's a difficult environment to sample in, and your population estimates have huge variance. So I'm of the school of, when I see a signal in this system, I am very surprised and happy that I got a signal. But the second part of your question, do I think more of that kind of study are worth doing? Of course. Trying to take new approaches to find ways to get data to tell you something. We have all this sampling in this ecosystem, really a tremendous wealth of knowledge and data, and trying to get that data to give you important management lessons. Of course, I think that's valuable. The question that I would have is, how long do you wait before you say we have an answer that we can act on provisionally? You can always modify it later, but are we going to wait until the 40th study, or are we going to be done with, after 4 or 5 really comprehensive studies done in different ways, all you having to rely on very similar data, which is not very good, coming up with similar answers? I'm sort of convinced that that there's an effect on delta smelt abundance, that was what those studies were about. There are other effects that I mentioned. Yeah. That's convincing enough to me that there's reason to take this problem seriously and begin to address it.
Yeah. Do you folks have any thoughts on that?
Yeah, let me offer my perspective. When I first started working on Bay Delta issues, the state of the art was really a piece of graph paper, a pencil, and an XY correlation. And that was really the end of most of the analyses that were being applied to the data that we were collecting. Over time, I've seen a really positive trend in starting to look at this more from a life cycle perspective, to ask questions about what are limiting factors, what are the mechanisms affecting some of the relationships that we're starting to see. I think it's a good organizing framework for helping us better understand the data that we're collecting. And importantly, I think it's a good framework for identifying areas of uncertainty and targeting additional research, additional analyses, and additional data collection that help us basically fill in some of those gaps. And so I see it as an important analytical tool. I see it as an important organizational tool in terms of how we approach some of these issues. Like John, I think it's a useful exercise in going through. It adds transparency and allows people to actually look at the information we're collecting from different perspectives. I think there are some differences of opinion, and I see that as healthy because that helps us sort out some of those differences and identify areas of agreement and disagreement. I think it also helps us establish a management framework for testing the performance of some of our ideas. And so I'm supportive of the overall basic trend that we're moving towards in terms of better sampling, more analytical analyses, more timely analyses, and a more structured framework for analysis in the form of a life cycle model.
I'd like to follow that up with one quick management-related question, which is one of the things these models do, which the other kinds of research has more trouble doing, is they actually they purport to estimate quantitative effects.
Mm-hmm.
If you change flow by X, entrainment will change by Y. They actually make estimates like that. And my question again for both of you is, do you think that's useful to management? Are those estimates, those quantitative estimates, useful, believable?
Red button.
Is that working now? You hold it down, you push it down, and it'll stay down. You can make it go.
Okay. Yeah, the point I was going to make is related to what you just asked. We have, I think, pretty sophisticated models. They're getting better and better all the time. We have a new one in the wings that Dr. Newman is working on. I don't know if we've talked about it yet. But my concern is that the quality of our estimate of entrainment itself is still very poor. We know we count salvage, and we know what exports are, but we don't really know what entrainment is. Typically, people would say, "Oh, we'll multiply by 5 or multiply by 10, and that's entrainment." But we don't know if that's the correct multiplier, and we don't know if the multiplier is constant from day to day or circumstance to circumstance. I could conceive of scenarios where the multiplier is fairly low because you're pumping at high rates. The fish come into Clifton Court Forebay, they zip across, they're in the salvage the next day. But under low pumping conditions, there may be a very high ratio between what comes into the forebay and what comes out the other end. And I feel like we need to get a better handle on what entrainment is itself, so we're actually modeling, the quantity that we're most concerned about. And I've been making a push recently that instead of trying to extrapolate so much, away from, using densities 10 miles away and then assuming they all end up in the pumps with no behavior, or trying to extrapolate from salvage upward to what came into the forebay or what came into the general vicinity, is to try to measure this directly by looking at densities that actually are entering your system. And then that's your number. And so I think that as we get a better handle on entrainment, we'll start to feel more confident about whether we know the impacts of entrainment on abundance.
Thanks a lot. Do you have any thoughts on that? I could repeat the question.
I think I got the nature of your question.
Okay.
If you have a conceptual model of how any problem works, it's our job to hit that conceptual model with data and see how wrong it is, right? And then refine your conceptual model. And when you begin to see various people from various approaches taking slightly different conceptual models but having results that support certain aspects of those conceptual models, a la increasing exports, increases entrainment, then that's an important finding, right? That tells you something about reality. The next step, though, of saying, oh, now I can predict the future with my model is sketchy in biological exploits, but it's also not necessarily that valuable. If you get a regression line of export entrainment, do you really think the slope of that line, not you, but does one really think the slope of that line is the number? That's, this much volume of water equals that much entrainment? That's not how I would use those results. I'm more interested in the conceptual models that these modeling, numerical, quantitative modeling exercises work on are those conceptual models supported? You know, I had a advisor once who said, after a long explanation about an intense ecological experiment involving mesocosms and how things were going to be worked out statistically, he said, you don't have to separate the hydrogen from the oxygen to understand the behavior of water. And I think that that's somehow in this conversation, not this conversation, but the larger conversation about entrainment is where we're going. Like, oh, unless we can predict this down to the nth and have a beautiful conceptual model that works every year on every species every time, then we don't know enough. I think we know enough about altered delta hydrodynamics to know that it's a significant problem for some species in some year types, right?
Yeah, but how good is a conceptual model to the managers? I mean, they have to decide how much to change the flow if they're going to do any changes, and what the benefit is by changing the flow, or changing the flow regime, or changing anything. They need some actual estimates of some kind, even though they're highly uncertain. So
yeah, I would agree with that, and I think that those models develop those relationships to the level of specificity that managers need, because the accuracy is important. For sure, and the more accurate, the better. But when you're dealing with continuous relationships, I mean, you always have a very difficult choice as a manager for where along that curve are you going to pick your point. And fortunately, courts of law, as opposed to courts of science, courts of law defer to agency expertise on those matters. I mean, they have to make a judgment. They make the judgment as best they can. They bring all sorts of experts into a room. They write biological opinions. The biological opinions get peer reviewed. They make a decision, and if they do a reasonable job of documenting that and using all the data at hand, and the best available data gets priority, then that's the decision. So, I mean, the only way to come up with a specific number where it's very clear that the number is this point on the x-axis is if you have a non-continuous relationship, right? If you have some sort of non-linearizable relationship, then it's easy because it's sort of binary. Here is low and here is high. But most situations are not going to be that way. So, in answer to your question, of course I agree with going forward, continuing to work these data, continuing to refine our conceptual models more. I would love in this system for the conceptual models to generate testable hypotheses so that we can sort between the different models which of the hypotheses, hypothesized outcomes actually contradict each other. I mean, that's how we would begin to sort through these conceptual models, is to find where they make contrary and irreconcilable predictions, and then take the opportunities when they come along. Nature provides the opportunity, do the test. That would help us make a lot more progress than more computing power, I think.
I've got actually a range of questions. I'm going to start with one which is kind of conceptual, because we've been banding around this statement of entrainment. I've been wondering actually what it means in the context of the delta. It seems generally, and maybe I'm misunderstanding what people say, that when they say entrainment, they mean what gets into Clifton Court forebay, and we don't know what that is. And we can measure some level of salvage at the salvage facilities. But if you actually look at the data, it suggests that for salmon anyway, those that are attracted or move into the South Delta suffer very high mortality rates relative to those that can stay in the Sacramento River or in the San Joaquin River on their way to Chips Island. So maybe a better definition of the entrainment zone would be the zone of influence of the pumps, so that when there's very high outflows from the rivers, the zone is relatively small. When there's small outflows from the rivers and high exports, that zone would be relatively large. Now that, of course, puts a very nebulous boundary on what constitutes entrainment, but I would be interested in anybody's comments on that. And sort of related to that, coming back to something that John had on one of his slides, was quoting a comment by Wim, and I think an exchange with B.J. Miller, that statistical significance is not the best basis for decision making. And of course, there are lots of social policy issues in which statistical significance is, we all know, is not a good basis for decision making. So if statistical analyses are not going to be the foundation for decisions about water exports, what should the decision rule be? And I think that also relates to this idea of, what's the entrainment zone and what do we do about it? So anybody want to comment? Then I actually had specific questions for Don and Tim.
Let me start on the zone of influence. I think from the information I provided, you can see very quickly where it is big and where it is small, and that has to do whether you've turned those rivers into a river and out of a tidal zone. Once you move back into more tidal effects, you can see basically from the data themselves that yes, there is an influence on the export pumps. If you turn them off, you'll have no salvage, obviously. But the real question, once you get moved into that other regime where you're more tidal, is what's the density of fish and how are they coming in? I think John misunderstood something I said, because I definitely don't believe and do not think fish follow the flow. It's exactly the opposite. I've been saying that for a long time. They're obviously very clever. They can get out of this system very, very quickly, and if they follow the flow, it would take months. They just can't move around by simply sloshing back and forth. But that's a start. So there are actually two parts to that. Yes, there's the part that is directly related to how much you're pumping there, but it's also related, the number of fish you get gets down to what that density is. And that's a much more complex issue, and you're trying to answer both those things at the same time. So no, you can't say on which day their fish are going to show up very well. But you can say if they do, what the salvage rate is going to be. So and then there's the relationship between that pumping and what has happened to the tides. Once you move further out in the system, it becomes much more tidal all the time, and then it fuzzes up very quickly. And it's the reason that when you move up into the San Joaquin River away from the pumps, that you don't see a direct export effect on the hydrodynamics. You see it a little bit, but it's so overwhelmed by the tides moving back that it's not evident. You don't see it very much in salinity transport, because just the advection part is becoming smaller and smaller, and it's more the tidal dispersion that's moving things around. It's unfortunately, that's what makes an estuary. It's where the river meets the tides. It makes it inherently complex.
I think the quote that I was reading from Wim was a little bit different than came across. As I read it, he was saying that statistical significance is not the most sensitive measure of biological significance.
Yes.
Right. So that there can be impacts that you're unable to detect with your statistics that are real impacts. So I think the situation is that we do have a number of investigations and models and workings up of data that do give us insight into what levels are protective, minimally protective of different fish at different times, and what levels are not. I mean, we don't have OMR restriction year-round to protect Chinook salmon. Why? Because they're not there year-round, right? So we have data, and we're honing down this problem using the data. I'm not suggesting that we just toss the data out. I'm suggesting that it's difficult to pick a point along a continuous line, and that when you're dealing with endangered species, the rules about making a mistake are a little different than when you're publishing a statistical result, right? The mistake that you don't want to make is you don't want the fish to go extinct. So you need to apply the precautionary principle, which the management agencies do, and that's how you proceed forward. It's not an easy job, but I'm not trying to suggest that it's data-free or model-free, or that the modeling can't be improved. But the fish are not behaving, they're trying to maximize diversity in their behavior. They're trying to maximize their variability. It would appear that's the strategy for a number of these fish. So they make it hard to determine when exactly the pump should be on or off. I'll also add that organizations like mine have participated in trying to develop things like a Bay Delta Conservation Plan, because the concept of being able to take water from different places, as long as there are rules about how much water you take, that might provide flexibility to work around different species and minimize take. It's just that it hasn't, the result hasn't come out to produce that effect yet. So there are solutions. They're difficult solutions.
Yeah, I wanted to address that a little bit as well. I mean, kind of philosophically, I have some problem with the idea that that we don't need evidence. I mean, what Wim was getting at in his comment was basically the concept that you could have a constant source of mortality, let's say, a couple of % a year for a species that's in a density independent part of its, population curve. And that if you kept whittling it away at 5% a year or whatever, then the subsequent generation would be 5% lower, and it would just keep on spiraling downward until you reached extinction, some years in the future. I don't know if that's how fish actually operate, whether there is true density independence or whether there are compensatory effects, or if the population, does it ever reach density dependency. The clock is reset and so on. But he was basically, that was the scenario that he was positing, that, entrainment that was very small but it was continuous would lead to extinction. And I don't know that that's certainly the DeRiso and Maunder had a bad reaction to that notion. It's something that's beyond my knowledge. I'm not a biologist. But just in general, I'm a little concerned philosophically with the idea that we would take actions without having any real statistical evidence to back them up, just based on kind of our own intuition.
No, I appreciate that, but I think we take those kind of actions all the time, but maybe not with Delta smelt. Don, in your introductory comments, you made a pretty categorical statement that there are all of these toxins that are entering the delta, but none of them is ever sufficiently concentrated to cause direct toxicity of fish. You did show that some of them could be really bad for some of the invertebrates. Then your slide showed there was something like close to 100 different pesticides with their various background products. It's several hundred, some of which you can't even analyze for. So I'm wondering how you can square that with your sort of categorical statement about them not being sufficiently concentrated to be toxic.
Okay, I didn't say there wouldn't be direct toxicity, to use your words. I said there wouldn't be acute lethality. In other words, the concentrations aren't high enough that you would expect to see the fish go belly out.
So I used the wrong phrase. Yeah.
Right, yeah, and I did not rule out the possibility that there could be sublethal effects. Probably one more sensitive would be National Fisheries Service has done some work looking at the effects of contaminants on salmonid olfaction and finding very low concentrations of things like chlorpyrifos or copper in the water changes the way the fish perceives its environment through the olfactory senses. And so I'm not ruling out those sorts of sublethal effects directly on the fish. But for the pesticides for which we have substantial amounts of monitoring data, that would be the OPs, the pyrethroids. Fipronil is a relatively new one from what we've seen. The concentrations of those that we find, if you compare them to the LC50s for salmon, steelhead, and any variety of fish, they're much lower. So I'm having to put aside potential synergistic interactions, which may be important, but we really don't have a very good handle on contaminant mixtures at all. But if you look at single contaminants, the ones that we measure, and compare the environmental concentrations we see to the concentrations that kill fish within a matter of a couple days of exposure, 24-hour, 48-hour, 96-hour LC50s, they're generally 1 to 2 orders of magnitude below.
So there isn't the possibility of pulses or pockets of high concentration that you just don't catch with your monitoring?
I hate to say that it's never going to happen, but from the work from the data I've seen, I think it's a fair general statement that I made, that the concentrations are below the short-term LC50s.
Okay, good, thanks. Then, Tim, I had a question about your really interesting Lagrangian experiment, and I'm just wondering if you you showed in your data that there was no response to the phytoplankton to the higher nutrient levels in the river with wastewater effluent, but I don't remember that you said why that was the case. I sort of my inference from what you said was it was probably that the production is light limited rather than nutrient limited, but is there some other factor there? And if indeed those extra nutrients are just carrying on downstream, what do you think happens to them in the end?
Right. So the chlorophyll A concentrations in both parcels drifting down the river looked remarkably similar in some ways. So, and there was a decline. So the abundance of phytoplankton upstream is a bit higher than what we're seeing downstream, and that's actually been shown in a number of studies. So why phytoplankton given a large supply of nutrients are not growing in the river? Well, in the cubitaners, they did show an increase to growth, and that's generally what we see around the country. When you have more nutrients, we end up with more phytoplankton growth. So, what's happening to those nutrients? There's coming out currently mostly in the form of ammonia. There's some nitrification going on, changing it to nitrate as it goes down the river over time through the bacteria. But it's entering into the delta. And there's a large nutrient load there as well. And, the delta is not a great growth area for phytoplankton. It's deep, the water's turbid and dark, and it's mixing around, so we don't generally have a large stratification event allowing the phytoplankton to bloom. When you get up into some of the back sloughs or areas, if there isn't clams, we might have some phytoplankton growth there using the waterborne nutrients. But there's efforts right now to understand how much of those nutrients are actually being used or transported from the delta down into San Francisco and other areas. But I think there's general agreement that there is an excess of nutrients, so it's not limiting phytoplankton growth due to a limitation of nutrients in the system. There is some question as to whether the excess might actually be limiting phytoplankton growth. But I don't, in the river itself, it wasn't a lack of nutrients that was changed. The presence of the extra nutrients was not altering the phytoplankton growth rates as far as we could tell between the two parcels.
If I could add a little clarification on that, and I'm not sure if in your study you looked at the rate processes. It sounds like when you're looking at chlorophyll is essentially a biomass measure, and I think a lot of what the Dugdale team found was that the ammonium is impacting the rate of uptake and the rate processes, and so I'm not sure if, if you collected that data and if that's...
Dr. Parker has collected some samples for uptake rates of the different nutrient ratios, and he's still processing that data. This is an ongoing experiment. So we'll get to find out rates later. John?
I think every project or activity should have a product or a commodity associated with it. And when I apply that standard to the presentations I've heard in the last 2 days, they sort of fall into two categories. There are presentations that have like a loss through mortality or tape flavor to them, and the products or regression equations or simulation model output. And it's very logical to me how those would relate to decision making, because you could use them for scenario analysis. The other category of presentations fall more into the production side, or the ecosystem restoration or species conservation plans. And I understand they're not as evolved as this first flavor of projects, but they also should have a product or a commodity associated with them. And I'm struggling to have a consistent concept of what that product might look like so that you could use it for scenario analysis, or in some form it would help decision makers make better decisions. So my question is really for Chuck's group. What is your expectations for what these products might look like that you were sort of alluding to or hoping for in your presentation, and what John and some of the USGS folks were giving us a little flavor of?
It's a good question. And when we look at, say, habitat restoration, it seems to me that there are different tiers of what you refer to as products, John, that we might be looking for. You know, one of the first tiers is just occupancy. If we create a habitat, do we meet habitat suitability criteria? Do we see evidence that the target species are even inhabiting that particular restoration area? Is there a trajectory that it takes some period of time, months or years, for that habitat to mature? And so I could see trajectories, I could see habitat use, and I could see just fundamentally, does this habitat meet our expectation in terms of suitable criteria for a given species? A second kind of a tier of product, if you will, is our expectation to a large extent is that many of these restored habitats are going to provide food production benefits. And we'd like to be able to say that the food production benefit from this restored wetland, in terms of food that's available for our species internal to the habitat, as well as exported from that habitat to adjacent waters, is positive, and that we're not creating a sink for nutrients or food production. We're not creating a sink for mortality, but we're actually creating a positive benefit. And so being able to actually monitor and predict that we're going to have those kind of positive benefits, to me, is part of the research and part of the development of the restoration strategies. Another element, I think, is, we're looking, and to kind of go to the, some of the core sorts of things, we've got levee restoration projects that incorporate large woody debris and other elements. And we want to see, as a product, do fish actually use those? Is there evidence that survival might be increased as a result of that cover habitat? Those sorts of biological mechanisms are hard to get your hands around, but they've been the metrics and the products in many restoration projects for salmonid habitat in the Pacific Northwest. And I think we need to start moving down that path a little bit, because right now we're dealing in many cases with projections or hypotheses as to how some of these restoration projects are going to operate. The other, to me, is we've had a couple of comments that have been made by various presenters that they're surprised that given the existing habitat conditions that we currently have, that we even have survival, that these are even viable habitats for some of the species. The riprap channels, the high predation rates, some of those things. And so it seems to me that there are a couple of fundamental products that also come from that sort of effort. One is, in essence, a demonstration to be able to prove the concept that these restoration projects improve habitat conditions above our baseline. And I think that's both a scientific product, but I think it's also a product from the standpoint of the managers. Many of the managers are looking at these products and saying, do they actually provide the kind of benefit that we thought they did? And one of our products, I think, should be a test of that sort of linkage and that sort of performance at various metrics. And so I think there are a whole range of quote-unquote products that can emerge from that kind of a process. I'm concerned that if we don't take action in some of these elements that we think are high priority, that we're going to lose opportunities. And so I don't want the product itself to end up delaying extensively the process. I think there's an element of risk involved in some of this as well, and we're going to need to go out and test some of these things. There'll be some things that were wrong, and there's some things that were right. And I think through the presentations like what John described and others have yesterday and today, I think we've got some good insights into at least where we might put our best bets in terms of getting positive products that will help pay off.
The subject of this workshop has been interior flows and related stressors, and I guess I want to come back to the related stressors and ask John a question, and perhaps also Don. I heard that dissolved oxygen may be an issue in the lower delta, and I guess that's the first I've heard of that. I'm not as current in all of the literature, which is voluminous, but when I think of the system, I think it's very different from the Chesapeake Bay, where we do have low dissolved oxygen issues, and all of the characteristics of the bay that lead to low dissolved oxygen characteristics are different here. So can you help me understand how that sets up? And thinking about it in a broader sense, then how does that fit into some of the other stressors that we've been considering, like flow and entrainment and those kinds of issues? How important are they? I'd like to hear your thoughts on that.
Okay. So the dissolved oxygen problem that I was talking about specifically is in the area of Stockton, where the San Joaquin is flowing, has already flowed into the delta. There's a ship channel that's been dug so Stockton can have a ship port, and in constructing that ship channel, making it really deep, right, and really wide, that combined with the low flows from the San Joaquin side, the low velocity of flow, combined with the fact that most of that flow is agricultural return waters, which are obviously charged up with all sorts of nutrients, you get this sort of lake. The San Joaquin comes in, there's not that much flow, there's a lot of biological oxygen demand, and so historically you've gotten these dissolved oxygen crashes. They happen throughout the year. They happen mostly in warmer times of year, obviously, but the concern there has been that if they're happening during times that are critical for migration of salmon, particularly fall run Chinook salmon coming in at the low flow, kind of warmer end of the year, that they form a migration barrier. They also happen, these low dissolved oxygen events also occur in the spring and in the winter historically. There's been a fix to that of sorts, which is to add a dissolved oxygen bubbler at the port, to try and aerate the water a little bit. But the problems there, there still remain dissolved oxygen problems, occasionally less frequently than in the past because of that bubbler. So my point there was just to say that there are these export pumps that get a lot of attention. They get a lot of attention because there are bodies there. But there are all sorts of hydrodynamic problems, many of them related to the pumps, not all of them related to the pumps, that are caused by low flows coming in, as well as the water quality coming in.
So how do we think that things like that seem very localized in the big picture?
Right.
How important are those factors, that and the contaminants issue?
So I'll obviously let Don speak to the contaminant issues, and I just want to emphasize that I'm not saying that any one of these things is the one thing that you fix it and you're done. Right? There are a lot of problems here. The low dissolved oxygen is localized, right? It's like, oh, that's a small problem. That shouldn't be a big deal. But it's at the mouth of the San Joaquin River where it's coming into the delta. So fish that are going to the southern part of the San Joaquin or the southern part of the Central Valley need to get through that junction point. And so, the dissolved oxygen problem, you solve it with the bubbler, but the underlying problem is still the same. You have this very low flow coming into a lake-like environment with very poor water quality at an important junction point. Every fish in the San Joaquin Valley that's migratory, that's anadromous, has to go through that point. So it's a localized problem that has a lot of leverage. It's not like as if it were up on the Tuolumne River somewhere. That would be localized with localized impacts. This can have more wide-ranging impacts, and it's related to inflows to the delta and water quality of those inflows.
If I can add on the dissolved oxygen in the Stockton ship channel, a great deal of that low DO was due to ammonium discharges from the Stockton wastewater treatment plant, which is upstream. That ammonium, as it's being nitrified, is consuming oxygen. That treatment plant has upgraded and is now nitrifying it. And much of the dissolved oxygen problem has been solved with that, to the point where now the bubblers are able to keep up, is my understanding. There's also some localized dissolved oxygen problems in the Sassoon Marsh area when some of the duck clubs are discharging the water from their marshland into the channels there. And again, that's another localized area, but also in a rich biological environment.
So I have a question. I wouldn't mind getting a couple different perspectives from. Oh, sorry.
Yeah, I won't say anything further on the dissolved oxygen. The Stockton situation is the one I'm most familiar with. I actually did my graduate work at FIMS, which I think is your home institution. So I'm familiar with the situation in Chesapeake Bay, where you have much greater geographic extent of low DO than we do here. Here it's really the Stockton issue. But as far as your part B of your question of sort of how do contaminants fit into the big picture, the places where we can tie, kind of maybe going on a limb here. I've talked about where we can tie contaminants to a specific effect in a number of places throughout the delta. American River, I gave you an example of pyrethroid input from urban runoff, creating toxicity to at least the most sensitive invertebrates that live in that stretch of the river. Cache Slough, again, urban, supplemented with agricultural runoff, causing toxicity to Hyalella, possibly even the coke pods which smelt feed. I'm doing some work in Sassoon Marsh, and there's no shortage of toxicity or pesticides going into Sassoon Marsh and the creeks. What effect that's having in the more marine waters, at least brackish waters of the marsh itself, is a tougher one to address. But in terms of finding acute toxicity and linking that to a specific substance, whether it's pyrethroids, fipronil, that seems to be more of a discrete location. Sassoon Marsh, Cache Slough, American River, I could probably think of a few others given some time. More of a broader picture, maybe the larger water bodies of the delta, where Old River, Middle River, Sacramento, San Joaquin. We don't really see the toxicity with our current toxicity testing tools, but we do see things like histopathological conditions or biomarkers of a certain enzyme that seems to be unusually high that can be induced by contaminants, but it's hard to say it definitely is due to contaminants. There, the linkages are a little less clear. And as I indicated, we're dealing with 160 pesticides. We're only monitoring 45% of them. There's the whole interactions. The USGS has done a lot of chemistry on those waters, and it's typical to find a dozen pesticides in a given water sample. We know nothing about how pesticide A is interacting with B, let alone adding C, D, E, F, and G to the mix. So it's a very complicated soup out there. What effects we do see tend to be more at the histopathological biomarker level rather than mortality, rather. And it's really harder to tease out what the causative factor is, given the extent of the data. So it's hard to answer your big, how big a picture is this?
There is, though, on that bigger picture, I mean, some people don't think of nutrients as contaminants, but to the extent that humans have changed the nutrient mix in the delta, I think that the nutrients, there's certainly a growing body of evidence that the changes that we've made to the nutrient mix of this delta have had some broad impacts on the system. From, we've been increasing ammonium relative to nitrate. We've been increasing nitrogen as phosphorus is going down, and those changes support a different food web than what was historically supported under a very nitrate-balanced N-to-P system that used to exist here. So I think that the changes we've made to nutrients does have that broader influence on the system.
So my question that I would like, trying to bring us back to, I just reread our charge a minute ago. And no. And I was just sort of thinking about something that was motivated by thinking about the consensus, pretty strong scientific consensus with some objection. I think, Chuck, you were at the X2 workshops back in Tiburon a long time ago.
I was.
And I think one of the things that was in that everyone agreed that qualitatively we could see that there was an effective flow, but it was hard to be much more certain given the nature of the data, which certainly has improved a lot since then. We've had a lot of data points. But it seemed like that Bruce developed a really interesting strategy trying to say, okay, how can we make things look as much as possible as they might have looked naturally in terms of X2 variability, given probably 30 million people in California at that point, and that existing agricultural structure, all of that. So my question would be, and I'd want a couple reaction is, suppose that we could get a broad consensus on, say, Paul's new model of unimpaired flows. I mean, things like Dayflower model, so having an agreed-upon model for unimpaired flows. Suppose there was such a model created that everyone could buy into and probably, was sustainable, was defensible. Do you think there would be the science sufficient? Is there sufficient scientific evidence now to support some sort of unimpaired flow percentage-based standards that would be sort of like, okay, water guys, you get to define what unimpaired flow is. Now the regulatory guys will step in and use your estimate as a basis for creating standards. Do you think that's something that we have enough scientific consensus to say there is a policy, the slider for policy on how protective to be? That's a policy decision. Do you think there's scientific enough evidence, though, to make something along those lines?
It's kind of a simple no, and here's the problem. Is that when you go back to what natural flows were, you got into the kind of thing that John Bureau presented. When you have these flood events, they didn't come ripping down an armored channel and canals into the delta and zip right into the bay. They went over the banks, they flooded vast areas, there was a whole different scenario. And that gets into some of the stuff that Paul has done and looking at how those flows work their way through the system. So just throwing we take the unimpaired and we'll throw that in there when it zips right through the system, and it doesn't have anywhere near the kind of ecological benefit that it would if it were flooding areas, wetlands, creating wetlands, vernal pools or whatever during certain times of the year, and totally different kind of ecosystem later. So it's just throwing water. That's what a lot of people say. You just throw water at the problem, you're not going to get where you want to go. There's a paradox there too that you will, and the problem is both these things are true. That the system absolutely needs more water, but putting more water in it won't necessarily change the populations, and it's because of all those other factors that come into play. It's just too altered. You won't get the kind of response you're expecting.
Paul?
Yeah.
You were citing me, so I feel.
If you want to, sure.
The difference, I think. Sorry.
Here.
I think an important difference to bear in mind is that comparison is that with X2 we had relationships that held up and have continued to hold up in the 2 decades since we adopted those. So that X2, we don't know the mechanism at all, but it still is. When X2 is a small number, we get lots of fish, and when it's a big number, we don't get so many fish, and invertebrates and the rest of that. And that was what was uniting people behind it, is that, no, we don't know what it should be, but it really does seem to be related to stuff. And there's a little bit, I think, of agreement that the stabilization of inflows that has intensified over the last 15 years is not a good thing. So maybe variability, and California's climate is intensely variable, so percentage of inflow is attractive for that. But I think you would have much more difficulty identifying what that slider is here, because we don't have a response variable for some of the reasons that Greg just described. It's operating, it's a characteristic of California, but so many other things have changed that whatever signal is in that is not as obvious as the X2 signal continues to be.
I didn't realize that Greg and I were going to...
Paul, then John.
Okay, sorry.
Yeah. I think I'll expand on what Greg said, and I would also answer. I would also answer no, because when we're talking, it's really the flow integrated with the landscape, and as Greg said, we don't have the natural landscape both up in the upstream watersheds nor in the delta itself, as we heard from John Bureau earlier. We saw how the landscape in the delta was so much different, the landscape and the channels, et cetera. So this would go back to why did we start looking at this issue of natural flow? I think it's, even though the answer to your question is no, I think understanding the natural conditions is still valuable for 2 reasons. One is we've been talking about restoration activities. So what is our metric to what are we trying to restore? And we believe that if we understand how the natural system functioned, how did the flows interact with the landscape, that some of those flow functions are the types of targets that we should be looking for when we design restoration activities. The second goal of this effort was to demonstrate, compare differences between this concept of unimpaired flow and what the natural flows are. So, I think I'll speak for where I think we are in our work. There's a lot left to be done. Certainly, there will be a lot more to be done in terms of understanding flow function and how that should be integrated into habitat restoration. However, I think we've got far enough in this project to be very definitive to say that the unimpaired flow calculation is not in any way a good representation of what the natural flow conditions were. So that, I think, to go back to what the state board and in their flow report recommending that metrics be based on the a percent of unimpaired flow, I would offer up my opinion that based on the work that we've done, that the unimpaired flow calculation does not in any way represent natural flow conditions, and therefore it would not be a good metric for regulatory purposes.
John?
So I'll give you an unqualified yes, and then I'll give you some qualifications. But let me explain the yes. The relationships that we have between flow into, through, and out of the delta and biological response are strong and statistically significant and hold over decades through clams and creation of pumps, etc. We see those relationships now. We see that Chinook salmon survival through the delta is better at high flows. We see longfin smelt population responds at high flows. We see things further downstream, further upstream, split tail spawning on floodplains, right? A result of higher flows. So I take Greg's point and Paul's point that the landscape now is different. And so the landscape that these flows are going through, the notion of full natural flow, natural has quotes around it because are we talking historical natural going through the flooded landscape with long retention times, or are we talking about the natural flow, meaning what would happen now without human facilities in the way of that flow? The latter, the flow that we see now, produces strong biological effects. It's the strongest signal we have in the ecosystem. It explains more different species and more different positive responses than any other single thing. And we have the capacity to restore the landscape. That's a beautiful thing. So I hear people say a lot of the times, we're never going to be able to get back to X. We're never going to get back to the historical situation. I mean, you got to accept that things are going to be bad from now on, a little bit. And I don't buy that. I buy it for certain species, but I don't buy it for split tail. You could restore the landscape, the floodplains, and provide the flows. You could have more split tail than you have ever measured in the history of measuring split tail on this landscape. And that would be a good thing for split tail and things that eat split tail. You could have more longfin smelt than you've measured if longfin smelt responded to the physical, the modification of the physical habitat, which there's no evidence that they do. But salmon, we can restore the landscape that these fish migrate through in the delta, take out some of the riprap, restore some floodplain alterations, and improve the flow. The sky's the limit. We've been measuring the response of organisms to flow since the landscape became relatively fixed and fully modified. We still see the flow effect. We haven't begun to experiment with the restore the landscape aspect of it. So I think that the flows that we have now, the unimpaired flows, produce their effect, and by setting doing a percentage unimpaired flow approach, you do a few things. You put more water back, depending on what the percentage is, but you importantly restore the timing of the flow, which is very important in terms of behavioral cues and ecological processes in the system, and you balance the impact of nature's variability among water users and species. Right now, it's distinctly imbalanced. Right? If I showed you a graph of what happens to unimpaired flow in dry years, the environment gets less of a percentage of whatever the natural flow is than it does in wet years. Because in wet years, it's a flood, and we can't control it. We have flood releases. And in dry years, human needs turn out to be pretty inflexible. And so, we get much drier conditions at the worst possible time for the fish. So the percentage approach would balance out that risk. The caveat that I'll add into my uncaveated yes is that there are certain situations where the fish are in a different place than they would have been historically with the, quote, natural flows. And, I'm thinking of winter Chinook salmon above Shasta Dam, right? So if you produce the natural hydrograph below Shasta Dam, you're going to wind up with winter Chinook salmon spawning in very low hot water because they're spawning in summer. They used to spawn way up in the Pitt River, all right? There are going to have to be modifications to the full natural flow paradigm to account for changes in the landscape that we're not going to undo, all right, or differences that have come about since the last time we had a natural flow event. But I would much rather start from a conceptual framework of this is what fish evolved to, this is the and wildlife and ecosystem processes, that this is the pattern of variability, this is the timing, right? This is the range across year of flow variation. I'd rather start with that template and then tweak it than start with the regulatory and human economic demand landscape that we have now and try and tweak that back to some other thing. I think that's a much longer path to success.
Well, thanks. I bet.
Let me qualify and I agree a lot with what John said. I wanted to make sure there wasn't taken out of the context I was putting this in. I'm thinking in terms of the levels of flows that I'm expecting to come out of a decision. I don't think they're sufficient. It's very clear that flow has a big factor. In particular, everybody likes to talk about the pelagic organism decline, but there was a huge pelagic organism rebound following the last drought, 95 through 2000. What were the characteristics? It rained like hell for 5 years. Thank goodness for those of us who negotiated the accord, because it kind of put off the hit. It got through that, but all those species came back very strongly, except for over by clam. Their population went way down during that period. It kind of, so is it just flow, or was it they just wiped them out because they got stuck with fresh water for a very long period of time? So yes, flow can have a very, very big factor, but in terms of the kinds of quantities I expect, I don't think it's not without doing a lot of other things. Yeah, if you took away Shasta Dam, allowed the salmon to go all the way up the Pitt River again, and then flooded the valley periodically, which would occur because one of its big purposes is flood control, yeah, whole different story. But really what it takes in terms of flows to really get things going are the kinds of flows you don't control with pumps, or you can control them with dams because you're stopping them, but then it's a very, very big economic disruption to take the kind of flow that I think really takes to really push the fish back. It's going to take a lot more than that. That's where it comes back to, yes, the fish absolutely need more flow. It's beneficial for them, and if you do it at the same time, you probably won't see much of an effect because of all these other things.
I'm gonna have to cut you off here. I know we could go on like this for a long time. And
20 years.
We never solved this problem, so we're always having this to do.
Yeah. So, it's been a great discussion, but we do have to have our public comment period. So I'm going to go ahead and do that now, and I'm going to thank all of the presenters today. It's been a great discussion, and I'm sure this will be the last word in any of these discussions, so we'll get all the answers. Anyway, I have 2 blue cards. I don't know if anybody else want to make a public comment, but first public comment is Steve Ottemuller with Friant Water Authority.